run.
When the James Webb Space Telescope was launched at the end of 2021, we expected stunning images and illuminating scientific results. So far, the powerful space telescope has lived up to our expectations. It has shown us things about the early universe we never anticipated, and those results are forcing a rewrite of astronomy textbooks. Join us as we dig deep into how James Webb just shattered our understanding of the cosmos. The early universe and its transformations are fundamental to our understanding of the universe around us today. Galaxies were in their infancy, stars were forming, and black holes were forming and becoming more massive. The Hubble Space Telescope was limited to observations at about z equals 11, which is roughly 400 million years after the Big Bang. But James Webb has shoved that boundary aside, orbiting the Sun around a stable point 1.5 million kilometers from Earth. Webb's giant gold-coated primary mirror, which is as tall as a giraffe, is protected from the Sun's glare by a tennis court-sized sun shield, allowing unprecedented views of the universe in infrared light. James Webb is now studying galaxies stretching back to at least 290 million years after the Big Bang. And later this year, fresh data releases from ongoing Webb galaxy surveys should push this record back even further. Such early galaxies are not in themselves surprising. Astronomers expected that first star clusters sprung up shortly after the universe moved out of the so-called Dark Ages, the first 400 million years of its existence, when only a thick fog of hydrogen atoms permeated space. But the galaxies found in the Webb images appeared shockingly big, and the stars in them too old. The new findings are in conflict with existing ideas of how the universe looked and evolved in its early years, and don't match earlier observations made by Webb's less powerful predecessor, the Hubble Space Telescope. Observing more and more galaxies at times that barely succeed the supposed origin of the universe raises serious questions about the viability of the Big Bang theory. How could bright, fully formed galaxies exist at what in cosmological terms would be regarded as a mere moment after the universe came into being? It is like watching an adult emerging fully formed from childbirth. According to the most widely accepted models of galaxy formation, giant galaxies are formed from small, faint clouds that gradually coalesce through cosmic mergers. This process takes billions of years. At a time when the universe was supposedly in its infancy, the theory predicts only the faintest dwarf galaxies, so small and faint that we would barely expect to see anything at all. Only later would giant galaxies form from cosmic mergers. And yet here, in the very first images sent back by James Webb, we are already confronted with galactic behemoths, giants that simply could not have formed in the time allotted to them in the established theory of the Big Bang. Put simply, James Webb is defying the supreme theory describing our cosmic origins. And that's not the only time James Webb has challenged our understanding. One of the biggest and most heated cosmic debates of our time surrounds a peculiar dilemma with a rather snappy name: Hubble tension. This phrase describes the fact that, even though scientists are aware the cosmos is constantly ballooning outward in every direction, as we can clearly see stars and galaxies drifting farther and farther away from us over time, they can't perfectly pin down the rate at which that ballooning is happening. And the rate is accelerating, by the way, a startling discovery astronomers made in the late 1990s that could be due in part to the existence of dark energy. That leaves us with a pretty major chasm in our understanding of the universe. In an attempt to get to the bottom of this, researchers announced that the James Webb Space Telescope has weighed in on the situation for the first time. But it did not solve the mystery. In fact, the telescope actually thickened it. But how? In fact, the Webb telescope has double-checked the work of its older sibling, the Hubble Space Telescope. Hubble's measurements of the expansion rate of the universe are exemplary. The trailblazing observatory found, further ratcheting up the Hubble tension. Putting it simply, Measurements of the expansion rate of the universe, defined by a property called the Hubble constant, just don't add up. On one hand, observations of the cosmic microwave background radiation, which is like a baby picture of the cosmos from just 379,000 years after the Big Bang, say the universe should be expanding today at a rate of about 67.8 kilometers per second per megaparsec. This means that every volume of space a million parsecs, or 3.26 million light-years, across should be expanding at a rate of 67.8 kilometers every second. An alternative way to measure this expansion is by climbing onto the cosmic distance ladder, where each rung is formed by a different astrophysical milestone, such as Cepheid variable stars and Type 1 supernovas. How bright these objects are can tell us their distances, which we can then compare to their redshift values to determine how much the universe has expanded while their light has been traveling to us. However, the problem is this method gives us a completely different value of the Hubble constant, somewhere around 73.2 kilometers per second per megaparsec. The apparent paradox between the two measurements is what cosmologists have started calling the Hubble tension. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error on the bottom rung of the cosmic distance ladder, which is home to the Cepheid variables. These are stars with luminosities that predictably fluctuate as the stars pulse in and out. The longer the pulsation period between moments of maximum luminosity, the greater that maximum luminosity is. This period luminosity relation allows us to accurately calculate their distances to Earth. It's possible to measure the pulsation period to calculate maximum luminosity. Then, based on how bright a Cepheid variable appears in the sky to us, we can work out how far away it must be to appear that bright. But it's not quite a foolproof method. The Hubble Space Telescope is able to observe Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, there was a concern that unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheids' apparent brightness values, creating an unseen and systematic error in the measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our vantage point on Earth. But new measurements achieved with the James Webb Space Telescope of 5 galaxies, hosting a combined total of more than 1,000 Cepheid variables, have ruled this possible error out. Webb's infrared vision is able to cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables, so they stand out from the crowd. From these Webb's measurements, astronomers led by Adam Rees of Johns Hopkins University determined that Hubble's original measurements were spot on. With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. However, the puzzle of expanding universe is only the tip of the iceberg. In a deep look at our vast space, NASA's sharp eye on the universe may have caught sight of dark matter, which is believed to constitute most of the material universe, but it cannot be seen by conventional telescopes. We can chart its presence through gravitational effects, such as when a massive galaxy passes in front of a distant star and magnifies the light. Dark stars may be fueled by particles of dark matter, just as normal stars like our Sun are powered by normal matter. Dark stars, if they do indeed exist, may be key to helping us understand how the universe first got light. For about 15 years, scientists have speculated that dark stars were among the first our universe ever produced, when it was just 700 million years old. Their interesting moniker comes from the song Dark Star, first played in 1967 by the Grateful Dead, the research team that first predicted dark stars told Space.com in 2009. Another inspiration was Crosby, Stills, Nash, and Young's 1977 song, also called Dark Star. And observations from James Webb suggest that the 3 distant objects, which all are from early in the universe's history, meet the key characteristics of dark stars. They are luminous, but too cool for fusion to be happening. The three candidate dark stars, known as JWST Z13-0, JWST Z12-0, and JWST Z11-0, may be the target of future Webb's observations to look for dips or excess of light intensity in certain frequency bands that may match other predictions for the energy of dark stars. In addition, James Webb has already thrown other strange puzzles at researchers, such as demonstrating the number of galaxies in the early universe due to cosmic rule breakers. This discovery sheds light on how early galaxies evolved and the fundamental processes that shape the universe as we see it today. To discover the truth about these cosmic scofflaws, a team of astronomers used the James Webb to gaze over 12 billion years back in time and observe galaxies, as well as the rules they followed through cosmic history. The crew found that the same set of rules continuously prevailed, connecting the rate of star birth to galactic masses to chemical compositions. But these rules traced only so far back. The earliest galaxies defied them. As Claudia Lagos, an associate professor at the University of Western Australia, said in a statement, "It was like the galaxies had a rulebook that they followed, but astonishingly, this cosmic rulebook appears to have undergone a dramatic rewrite during the universe's infancy." The most surprising discovery was that ancient galaxies produced far fewer heavy elements than we would have predicted based on what we know from galaxies that formed later. This disparity hadn't been spotted before because instruments used prior to James Webb hadn't been powerful enough to see the chemical makeup of galaxies as far back as around 11 billion years ago. However, the telescope allowed this team to look back to just a few 100 million years after the Big Bang, which showed a break in the relationship between star formation, mass, and chemistry. When the universe first began to form the first stars and galaxies, it was filled with hydrogen and helium, the two lightest elements, with the former being the most dominant by far. Only a smattering of heavier elements, which astronomers call metals, existed until the first generation of stars forged them at their hearts and then dispersed them through the universe at the end of their lives via massive supernova explosions. This material was eventually incorporated into the next generation of stars, meaning these stars, and thus the galaxies they sit in, had a higher concentration of metals, a measure called metallicity. That process of metal enrichment has continued throughout the entire 13.8 billion years of cosmic history, meaning early galaxies are indeed expected to have lower metallicities than their modern counterparts. But even factoring this in, the team found that the metallicity of early galaxies was still lower than expected, much lower. As such, Webb's findings could challenge current models of galactic evolution and the mechanism that facilitated the development of the first galaxies. What's more, with the aid of the James Webb Space Telescope, astronomers have seen starlight from two early galaxies that host feeding supermassive black holes, or quasars, for the first time. The findings could eventually help scientists better understand how supermassive black holes quickly grow to masses equivalent to millions or billions of suns, and how they and the galaxies that host them evolve hand in hand. Quasars are some of the most extreme objects in the entire universe. Powered by supermassive black holes surrounded by gas and dust, some of which is accreted to the black hole, some of which is blasted out at speeds approaching that of light. Quasars emit so much light they can often outshine every star in the galaxy that hosts them combined. Almost every galaxy is believed to have a supermassive black hole at its heart, but not all of these are quasars. For example, the supermassive black hole at the center of the Milky Way, Sagittarius A, consumes so little matter it is equivalent to a human eating a grain of rice every million years. Thus, it is not feeding enough to power a quasar. The first quasar was spotted in 1963, and since then, scientists have unraveled the processes that power their immense emission of light. In the 2000s, it was discovered that the masses of galaxies and their supermassive black holes are related, with the mass of stars in a galaxy around 1,000 times greater than the mass of its central black hole. The relationship between the masses of supermassive black holes and their galaxies holds for galaxies with supermassive black holes with masses millions of times that of the Sun, and for those with central black holes billions of times the mass of our star. The connection between the mass of galaxies and the mass of their supermassive black holes may be related to the fact that both grow via a chain of mergers between galaxies that eventually leads to the black holes at the heart of those galaxies violently colliding with each other and creating an even larger black hole. Consequently, after numerous mergers, the mass of a galaxy will be around the average mass of the initial galaxy times the number of galaxies it merged with, while the central black hole mass will be around the mass of the initial black hole times the same number, leading to a roughly linear relationship. Another suggestion is that when a supermassive black hole feeds on enough material to become a quasar, the radiation it blasts out regulates the material available for both powering the quasar and for forming new stars. Thus, when the quasar runs out of food and stops growing, star formation also slows in that galaxy. Whatever the cause of this relationship, astronomers have been unable to determine if it exists for galaxies and their supermassive black holes in the very early universe until now. This is because, while the brightness of quasars allows them to be studied at distances of billions of light years away, it also makes the observation of dimmer starlight from quasar-hosting galaxies challenging. Ground-based telescopes struggle to distinguish the light from quasars and the light from stars in their galaxies due to the effect of Earth's atmosphere. From its position above the atmosphere, the Hubble Space Telescope has had some success in unraveling the light from these galaxies when they are around 10 billion light-years away. But to do this for more distant and earlier galaxies, astronomers have had to wait for the most powerful space telescope ever placed in orbit, the James Webb. The quasars J2236 plus 0032 and J2255 plus 0251 were observed with James Webb's main instrument, NIRCam, for 2 hours at 2 different wavelengths. The team took this combined spectrum of quasar light and starlight for both galaxies, and then separated out the quasar light to see the light from early stars in such galaxies for the first time. Remarkably, observations of J2236 plus 0032 and J2255 plus 0251 and their galaxies with the telescope have shown that the supermassive black hole galaxy mass relationship exists even in the early universe. Currently, this data alone isn't enough to reveal the origins of this mass relationship and how supermassive black holes grow to such tremendous sizes, but it will inform future investigations. The findings represent just part of Webb's observations of distant quasars, with the powerful space telescope currently observing a further 10 of these supermassive black hole-powered objects and their galaxies. Elsewhere, James Webb has made a cosmic discovery about rionization that unravels more of the mysteries of the universe's first billion years. Thanks to Webb's sharp eyes, an international team of scientists has successfully conducted the first spectroscopic observations of the universe's faintest galaxies during this formative period, offering insights into a fundamental question that has puzzled astronomers for decades. What powered the reionization of the universe? The era of reionization marks a critical phase in the universe's early history, a time when it was plunged into darkness, devoid of stars and galaxies, and enveloped in a dense hydrogen fog. This period ended when the first stars ionized the surrounding gas, allowing light to traverse the cosmos. Determining the sources of radiation capable of clearing this primordial fog has been a key focus of astronomical research for years. The UNCOVER program, which stands for Ultra Deep NIR-SPEC and NIRCam observations before the epoch of reionization, utilized both imaging and spectroscopic techniques to study the lensing cluster Abell 2744, also known as Pandora's cluster. The phenomenon of gravitational lensing, where the massive cluster acts as a lens, warping the space around it, magnifies and distorts the light from distant galaxies. This effect enabled the team to identify 8 exceptionally faint galaxies beyond Abell 2744 that would otherwise remain hidden from view. The revelations from this study are profound. The faint galaxies identified are found to be significant sources of ultraviolet light, emitting at levels 4 times greater than previously estimated. This suggests that these dwarf galaxies were likely the primary contributors to the ionization process. In the words of Irina Chemerinska from the Institut d'Astrophysique de Paris, this discovery unveils the crucial role played by ultra-faint galaxies in the early universe's evolution. They produce ionizing photons that transform neutral hydrogen into ionized plasma during cosmic reionization. It highlights the importance of understanding low-mass galaxies in shaping the universe's history. After all, as you see, Webb's discoveries are weighing down on the Big Bang theory. There is only so long that the theory's defenders can continue moving the goalposts in the manner that they have done for decades to force observations to fit their preconceived view. Genuine science progresses as theories are devised to explain our observations. An accumulation of inexplicable observations at a certain stage demands the revision of a theory. Here are 5 alternatives to the Big Bang theory. 1. The steady-state model. While it's difficult to speak of a before when discussing the beginning of all space and time, how can there be a before? The totality of matter exploded out of a compacted ball with density and intense heat approaching infinity, called a singularity. For unknown reasons, this singularity suddenly expanded in an unimaginably violent explosion, and the universe as we know it began. Bang's old rival theory is the steady-state universe model. This one denies the possibility of beginning and end for the universe, opting instead for a continually expanding universe that nonetheless maintains the same overall density. In other words, a steady-state universe is forever identical, but continually growing bigger in scale. In this model, galaxies, planets, and other forms of matter are locked in continual recreation, and since the density remains the same, old astronomical objects become unobservable as new creations take their place. This theory was initially proposed by Sir James Hopwood Jeans in 1928 and was further developed in the late 1940s by Hermann Bondi, Fred Hoyle, and Thomas Gold. The late cosmologist Geoffrey Burbage championed steady-state cosmology early in his career and was one of the last serious cosmologists to eventually abandon the theory, even after new evidence directly falsified it. However, instead of jumping on the Big Bang train, Burbage developed a new model, called the oscillating universe, according to which the universe undergoes many small Big Bangs, like the universe is on repeat. 2. The bouncing cosmological model. If or when the Big Bang happened, the universe expanded from a single point whose gravity and density approached infinity and has continued to expand since then. This is called the inflationary model. The bouncing cosmology, Big Bounce, or cyclic universe model involves a rapid, Big Bang-like expansion of the universe. But it adds a rewind function, accounting not only for expansion, but also contraction of the universe. A cyclical universe shrinks to a minimum volume, and then bounces back into a subsequent expansion. Another variant proposes a cosmos that only bounced once. In this one, the present-day universe came into being after an earlier contraction, extending into an infinite past of infinite dispersion. According to the single bounce theory, the universe of today will expand forever. This theory was first propounded by Juliano Cesar Silva Neves in a paper published in the journal General Relativity and Gravitation. Neves is a researcher at the Mathematics, Statistics, and Scientific Computation Institute of the University of Campinas, Brazil. 3. Plasma, or electric universe theory. In the electric universe model, gravity takes a back seat to plasma and electromagnetism. In this theory, plasma takes up an integral role in cosmological events and the fundamental order of the universe, proposing electric currents that flow along plasma filaments, capable of shaping and powering galaxies. These currents stream into stars, powering them like fluorescent bulbs. They induce the births of planets. The electric universe theory was first proposed by Nobel-winning physicist Hannes Alfvén in the 1930s. Alfvén argued that if plasma pervaded the universe, it could carry electric currents capable of generating a galactic magnetic field. He later won a Nobel Prize for his work in magnetohydrodynamics. However, there's no evidence for the electric universe theory, and it fails to meet the National Academy of Sciences definition of theory since it has no predictive power in the empirical world of natural events, with which we could witness physical signs of its presence. But regardless, it's gained popularity via a number of lay scientists and YouTubers in search of a simpler way to explain the universe. 4. The black hole origin theory. The black hole theory suggests the universe popped out of a black hole from another universe. In this model, we're living beyond its event horizon. This theory has been around for some time. Initially, researchers at Perimeter University presented a paper detailing how black holes might be the origin of our universe. In a different and more recent version from theoretical physicist Nikodem Poplawski at Indiana University, the observable universe is the interior of a black hole existing as one of possibly many inside a larger parent universe, or multiverse. If true, we could say every black hole is a doorway to a new universe. But since we can't cross the event horizon, there's likely no way to confirm or falsify the theory. 5. Simulation theory. A lot of people in Silicon Valley are fond of an idea that if true seems to trump all others, the possibility of living in a colossal simulation. This idea gained mainstream attention from movies like The Matrix and off-the-cuff comments from Tesla CEO Elon Musk, who said in an interview that it could be entirely possible, despite the absence of evidence. Scientists later researched this idea in 2017, but results suggest our universe is not the creation of a computer program. The study was done by theoretical physicists from Oxford University in the UK. The Oxford researchers looked into the possibility of creating a computer capable of computing everything in this universe. But such a hypothetical computer would need to be powerful enough to calculate the motion of every particle. Needless to say, this is a difficult calculation. For the computer to record the data of even a few electrons, its memory needs more atoms than there are in the entire universe, and with the addition of only a few more particles, the complexity goes up exponentially. Hence, it's probably safe to say we're not the product of an alien PlayStation. The Big Bang Theory remains the most widely accepted explanation for the origin of the universe. But in empirical science, no theory can last forever. The scientific model of the universe is constantly changing as advances in fields like quantum mechanics and gravity struggle to unify theories about the fundamental laws of the universe. But while the Big Bang model isn't completely proven, for now, it's the best possible explanation, using all available scientific evidence. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.